Hello everybody, welcome to part 2 of my Logical Volume Manager course. Okay, today we're going to cover RAID mainly. So the important thing is that we understand the theory behind all the different RAID levels. We need to understand the theory clearly, otherwise we can't make intelligent decisions about which RAID level to choose. We need to understand the implications of choosing one RAID level over another, be it performance, be it resilience. So that's what we're going to start with. Then we're going to look at thin pools and thin volumes, which allows us to allocate a certain amount of storage, in other words, actually reserve a certain amount of storage, but provision more than that amount of storage. In other words, kid our system administrators into thinking they've got more, or our application developers or whatever, kid them into thinking that they've actually been given more storage than they really have. And this allows us to efficiently use space, because invariably you waste space when you create volumes. You tend to create them larger than they need be to cover potential increases in size that may never happen. We're then going to actually demonstrate everything. So we're going to do loads of practical exercises. We're going to create all these different types of volumes, and we're going to look at exactly what it is we've created by introducing a number of commands that allow us to monitor our volumes that we've created, to figure out what type of volume a particular volume is, how much space it's currently using, etc., etc. So that's the master plan. Let's see how well it goes. Can I ask you to do me a favour? If you think these videos are okay and perhaps worth watching, can you like and subscribe? Because it'll sort of get the word out there. The way YouTube works is if no one likes it, they assume it's, they assume you don't like it. Seems reasonable. So yeah, do us a favour, like and subscribe, even if you hate it. Thank you. So we're on Logical Volume Manager Part 2, and we're going to cover RAID. Let's do it. So RAID stands for redundant arrays of inexpensive disks, although typically nowadays we tend to say redundant array of independent disks. The original white paper was actually presented for the first time in 1988, written in 1987, and it actually proposed 5 different RAID levels. It's quite an interesting paper to read. It's obviously way out of date, but you youngsters would probably find it quite interesting from a historic point of view. It's a piece of archaeology. It's actually quite quaint. But basically, the whole reasoning behind it was the fact, for example, in the white paper, they tell you about a disk drive called a Fujitsu Eagle. I used to have one. My company did. And it was a 600 megabyte 19-inch rack mount, and probably, I can't remember exactly, but it was probably about 10U. A huge, great thing, weighed a ton, 600 megabyte, not gigabyte, and it cost $10,000. So they were expensive. However, at the time, there were what were considered PC hard disks coming out, which were proportionally quite a bit cheaper, and therefore the idea was you could create logical volumes, or virtual disks if you want, of a large capacity using these small PC style disk drives using RAID. So that was basically one of the reasons. The other reasons was to give you resilience, because back then hard disk drives were unbelievably unreliable. So that's basically a quick background. That's where RAID comes from. It's historic. Let's have a look at what LVM can give us. LVM supports 6 RAID levels. All right, really it's only 5. Okay, for reasons we'll say in a second. Now, one of these RAID levels was not defined in the white paper, and that's RAID level 0. And that's because RAID level 0 is striping, which tries to give us improved performance, and may well do. But it's not redundant in any way, so it isn't really RAID, it's probably AID. RAID 1 through RAID 5 were defined in the white paper. RAID 1 is mirroring, which is where we have multiple copies of our data, typically 2 or 3 if the data is very important. RAID 10 is trying to get the benefits of RAID 0, which is performance, and the resilience of RAID 1, which is resilience. I mean, that's the benefit. So RAID 10 is actually RAID 1 plus 0. And what it is striped mirrors, and we'll see that in a minute. Now, RAID 2, 3, and 4 were all striping with error correction mechanisms, in my opinion, all of which were academic in nature and not really practical. RAID 4 apparently is in LVM. I've never actually tried to use it. Maybe we'll have a play later and see if we can set up a RAID 4 volume. But forget about it, because basically they say, yeah, it's in there, but well, nobody's tested it. We don't know if it works. And anyway, why would you want it? RAID 5 and RAID 6 are both stripes with error protection, or an additional disk space used for error correction. RAID 6 uses 2 error correction parity blocks and therefore can survive 1 failure and still be resilient, 2 failures and we still have our data, but we need to sort the problem out. Whereas RAID 5 can only support 1 failure and we still have our data, but we're now at risk. So, quick review of what we did in the last part. We created a logical volume, and we could create logical volumes that were larger than a single disk, extend their size, we could reduce their size. They're really flexible. So that's what we've seen so far. Right, so we're going to look at striped disks. So the first question is, why would I want to use stripes? And the answer is very, very simple. Disk drives, particularly spinning disk drives, are terrifyingly slow. They are glacially slow. They are horrendously slow. And this slide is trying to demonstrate just how slow they are in a way that a human can understand. So if you had a 1 gigahertz CPU, which would be considered slow, then that means its clock cycle is 1 nanosecond. So if we were to compare a hard disk drive, to take the worst case scenario, with the heartbeat of a CPU, which is 1 nanosecond, but convert that to a second, so 1 nanosecond is the equivalent of a second, then how long would it take to get to the data on our hard disk? And it's terrifying. It's 4 months. It is 10 million times slower, which is quite amazing. The point we're making here is that hard disk drives are horrendously slow. SSDs are actually a lot quicker, but they are also horrendously slow. NVMEs are a lot quicker still, but they are also horrendously slow. 100,000 times slower than the CPU heartbeat. Right, now I appreciate, because people are going to say, well, hang on, you can't compare the clock cycle of a CPU with the latency of a disk drive. No, I agree entirely. Then they don't map onto each other directly. However, this does emphasize the point that hard disk drives and SSDs and NVMEs are slow as hell. Let's look at RAID 0 striping. Remember, it's not redundant, but it gives us performance benefits. Well, it might do, and it probably does. We're probably going to get performance benefits if we are using, or if our data access is typically random rather than sequential. We will almost certainly get some benefits. And the reason is that in my example on the slide, we've got 6 disk drives. The CPU can, as it were, stack up requests so that it can go to drive 0 request data, drive 1 request data, drive 2, etc., etc. So it can make all of those requests. They're sequential as far as the CPU is concerned, but disk drives are so slow. Did I mention that? That from the point of view of the CPU access, those requests are almost in parallel. So the CPU makes requests to 6 drives almost instantly, and 4 months later, the drives all come back with their data. But it isn't redundant. Fine, we've made that point many times, but I'll just make it again. How do you create one? Well, it's almost identical to creating a linear volume, but you add 2 extra arguments. So we have to say what type is it, and we say minus minus type RAID 0. Hyphen hyphen stripes actually indicates how many disks are in this stripe. Hyphen hyphen stripe 6. Data VG is the name of the volume group, and that will create us a 200 gigabyte RAID 0 volume. Okay, so let's start off by looking at mirrors. Now, that's a slightly complicated looking diagram, but I do want to briefly introduce, and we'll cover it in detail later, the fact that when you create any logical volume of type RAID, then you actually effectively create an additional very small, typically 4 megabytes volume, which contains information such as our dirty region log, the state of synchronization, etc., etc. So it's like a housekeeping block that Logical Volume Manager uses. So that's a mirror. It's simply 2 copies of the same data. And how do we create it? You simply say hyphen hyphen type, specify what type you want, RAID 1, and then you say hyphen hyphen mirrors, but they basically specify a number of additional mirrors. So 1 means we've got a 2 mirrored volume. 3, which is not uncommon, because the problem with 2 mirrors only like that is that if we lose one of those disks or one of the logical volumes, then we are at risk. So if you've got very, very critical data, you might actually go for 3 mirrors. It's expensive because obviously it's 3 times as many disks. So what we can do now is use what we've just created, our idea. We can say, right, we can create RAID 10 volumes. And what we want to do with RAID 10 volumes, it's really 1 plus 0, is create a number of striped mirrors. It's very important to differentiate. Now, fortunately, I've got a diagram because it's a little bit confusing. We could create, theoretically, but Logical Volume Manager doesn't support it, we could create mirrored stripes, but we want to create striped mirrors for reasons we'll see in a minute. And a striped mirror is what RAID 10 is in Logical Volume Manager. That will give us the benefit of resilience and the performance benefits of stripes. And you can see the syntax below. It's very, very easy. Hyphen hyphen type RAID 10. How many stripes do I want? I want 5. And there are, we can say minus I instead of minus minus stripes. So that's wonderful. Now, the benefit of this, having 1 plus 0, is that you can actually have multiple disk failures. I mean, don't rely on it. In that picture there, we've actually got 3 failed disks. However, our data is still secure. It still exists. Well, it's not secure anymore. It's beginning to get very wonky, but our data still exists because we have valid copies of every mirror within the stripe. But if we actually lost 2 disks in the same mirror, it's game over. That's it. No, obvious, and it's obvious. So it's a bit of a roulette game. However, think about it. If you've got 5 disks, and if you were unlucky enough to lose 2 of them, statistically, you are very slightly less likely to lose 2 disks in the same mirror, hopefully. So, I mean, always the case that if you have a failure, you fix it as soon as humanly possible, otherwise your data is at risk. There's no such thing as RAID 01. I invented that, but this is if you actually created 2 stripes and then mirrored them. Why is 1-0 preferred over this theoretical 0-1? You've got 2 stripes. If you lose a disk in both stripes, 1 in each stripe, I should say, then you've lost your data. It's game over. RAID 5, now this is a bit of a kind of an eye full of stuff here, but it's striping with distributed parity. Parity is an unbelievably simple but effective error detection mechanism. On each disk, the data in a stripe on a disk is known as a chunk. And so what we do is on each stripe, and remember the stripe covers the entire number of disks that we have a parity chunk. And how do we create it? Yes, it's pretty obvious. Hyphen hyphen type RAID 5. hyphen hyphen stripes 6 or minus I6. RAID 6 is basically a similar story, however, there is an additional parity disk. The overhead in RAID 5 is one disk per stripe, or one disk capacity is a better way to describe it. The overhead in RAID 6 is two disk capacities. However, you can withstand a disk failure and you are still resilient. So that is the big benefit with RAID 6. Performance-wise, RAID 5, RAID 6 are going to be pretty much the same. However, we really do need to discuss what happens in the event of a failure. Now, in the case of RAID 5 and 6, in the event of a failure, then we have to rebuild the missing disk. And this involves a lot of overhead. For instance, to rebuild the missing disk, we need to read all five, in this example, all five remaining disks to recalculate the missing data. So we have to do a read of the entire stripe, do a calculation of the data from the parity, and then write it back to the new disk. This involves a lot of CPU overhead. It also involves a lot of I/O, as you can imagine. So recovery time is significant. It can take hours, many hours. It can take days, depending on how many disks there are in your stripe, and of course the performance of your disks and the performance of your CPU, etc., etc. So RAID 5 and RAID 6 can give you significant recovery time problems. Where RAID 6 really wins is that while you are recovering, you are still protected, whereas RAID 5 you are not. So RAID 6 certainly would give you less stress. It'd be a lot less stressful while it was recovering. So that is something worth considering. And quite honestly, nowadays, it's getting to the point where people are beginning to think that RAID 5 might be obsolete because, because of this massive recovery time. So bear that in mind. So I've written a simple script, and what this will do is create a volume of each type, which we can then use to investigate further how we can ask questions of Logical Volume Manager. It's a simple bash script. All it's going to do is, first of all, display all the different commands that we're going to run, and we'll talk about each of them and the different options that we're going to use. So the first one is a linear volume. That's the technical name for it in Logical Volume Manager. And it begs the question, why would I ever create a simple volume when I've got all these wonderful RAID type volumes that I could create? Well, it's ideal for things like a boot disk. I can increase that very easily and then simply expand the file system to fit in it. So that's one of the major attractions of it. It means that you future-proof your install. The other reason for liking it, in my opinion anyway, is snapshots. If I'm going to do an update to Debian or Red Hat or Ubuntu, whatever distribution I'm running, then there's always a danger, albeit slight, but there's a danger that it might all go horribly wrong. And snapshots allow me to roll back. So I always do a snapshot before I do an update. So the dev SDB at the end is optional. If I don't do that, Logical Volume Manager will choose on my behalf. Next, we're looking at a RAID 0, a stripe volume, not strictly speaking RAID because it's not redundant, but whatever. Okay, so we specify the type, RAID 0, and we specify how many stripes there are. In other words, how many disks are there for data to be stored on. And then the rest of the syntax is the same as a simple volume. And again, optionally, I can specify which physical disk I would like it to appear on. In my case, I really want it to appear on SDF because that's where I've created my 8 virtual disks. So that's RAID 0. RAID 1, which is a mirror. Nothing unusual here. We simply change the type to RAID 1. And we specify the number of additional mirrors, do you remember? And then the rest of the syntax is the same. Okay, RAID 10 is our striped mirrors, which we discussed a few minutes ago. So RAID 10 is we creating a number of mirrors and then striping them, which is why the number of stripes is half the number of disks, because each mirror uses 2 of the available disks. We've got 8 disks. We can only create 4 mirrors. RAID 5 as we discussed previously, is where we can have redundancy through an additional disk to allow us to store parity across all 8 disks. So it's important to note, we don't have an additional disk which has the parity on it. We have an additional disk to increase the capacity so that we can have the parity distributed across the entire stripe. Notice the only weird thing, apart from we changed the type to RAID 5, we actually specify the number of stripes as being one less than the number of disks to reflect the fact that we're losing one disk capacity. Okay, and again, I've specified that I want it on SDF. RAID 6 is RAID, like RAID 5, except you have 2 parity disks. And if you recall, the reason we find RAID 6 far more attractive than RAID 5 is the horrendous recovery time of RAID 5 and RAID 6. However, at least when we have RAID 6, if we lose a disk, we are still protected while we recover. So now I'm just going to run all those commands, the ones that are on the screen, and you'll notice that none of them take very long. RAID 5 and 6 tend to take a little bit longer. The reason RAID 10, RAID 5 and RAID 6 don't take forever is because it doesn't synchronize everything when you make the volume. What it does is synchronizes them in the background after all the volumes have been created. So you notice RAID 5 and RAID 6 take a little bit longer, not a hell of a lot longer, but a little bit longer to actually create. So now we have created a simple volume, a striped volume, a mirrored volume, a RAID 10 volume, which is our striped mirrors. We've created a RAID 5 volume, and we've created a RAID 6 volume. So total chaos. However, if we do an LVS, it's not chaos at all. We can see the volumes nice and clearly. It doesn't tell us what type of volume they are, but it's kind of irrelevant to day-to-day operation. Let me do an LSBLK. This is going to be terrifying because of what we've just created. Oh my goodness. It's now becoming a bit unmanageable. I'm scrolling back through, there are literally screens worth of stuff. So it does tell us the truth, but we'd be better off looking at some of the LVS-O options, of which there are 250. So we'll go through all 250 now, one at a time. No, we won't. It's all right. But, so LVS is brilliant. It shows us, by default, shows us pretty much everything we want to know. However, we can add to what it tells us. So for instance, I can add to the LVS a plus sign which says give me the default values anyway, because they're all incredibly useful, and then I can start adding options. And at the moment I only want to show one, and that is seg type. So let's look at what we get if we do that. We don't get anything. That's because we've forgotten the -O. Goodness me, you can't get the stuff. So we put a -O in front and now it'll work. So we get the default values anyway, and then additionally to that, at the end we get what type it is. Now we could do things like LVS name, oh no, I forgot the -O again, -O name, seg type. This could be really useful in scripting, so we actually just end up with a list of types, a list of volume names and what type it is. So you can do that. We can actually literally extract any information we want, create output which would be very useful within a script. But what I want to do now is finish this part off with an introduction to thin provisioning, which I think you'll find very interesting. So we're now going to cover thin pools and thin volumes. And you're thinking, thin what? Okay, this is based on the principle that the storage administrator has a certain amount of storage that he wants to make best use of, whereas the end user wants as much storage as he can possibly get. Right, he wants to future-proof against requiring extra space. He doesn't want the inconvenience of having to go and rejig all of his storage, etc., etc. So when you say to him, how much space do you need? And he says 1 terabyte. You know damn well that he probably only needs 500 gigabytes. But that's the principle of it. And it's based on allocation and provision. I'm not sure if this is technically correct, but it's my way of thinking of it. The storage administrator allocates a certain amount of storage. That means he reserves it. So that means this is for real. He then provisions a certain amount of storage to the user, and the amount he provisions may well be, doesn't have to be by the way, but it may well be considerably more than the amount that he's actually allocated. So that's the theory behind it. All right. The way you do it is a little bit weird. We're familiar with creating a volume group into which we put volumes. What we're going to do now is create a thin pool, which is vaguely like a volume group, only it's nothing like a volume group. It's actually a special type of volume. So we're going to create a thin pool. Then that will have a certain amount of space allocated to it. We're then going to create thin volumes in this thin pool, which are likely to actually have more storage provisioned to them than has actually been allocated in the pool itself. Let's do it. It might come a lot clearer if we actually do it. So the first thing we need to do is actually create a sparse pool, a thin pool. I'm going to call it sparse pool. I don't want to call it thin pool, otherwise it gets a bit confusing, because that's also one of the options. So I'm going to call everything sparse pool, sparse volume 1, sparse volume 2, etc. So LV create. We need to specify a size. I'm going to specify a ridiculously small size. This is what we're allocating, physically allocating. I'm deliberately going to choose a totally unrealistic size so that we can very easily actually see what happens if we under allocate and over provision. If we do that, what happens if the end user starts using space that we don't have? 100 meg is ridiculously small deliberately. So that's the argument to indicate that we want to create a thin pool. Then all we need to do is say where do we want to create it and what would we like to call it. Okay, so it tells us that we've created a thin pool called sparse_pool in the volume group data_vg. So let's follow that up with an LVS of data_vg. The reason I've done that is we can compare the attributes of this new sparse volume with our other volumes, and you'll notice they have an R at the beginning, which actually stands for RAID. So the first field of the attribute is the type. Okay, so we've created our sparse pool. Notice we have a T in the first field of the attributes, and that tells us this is a thin pool. Okay, now we need to create a thin volume within this thin pool. So let's do that. You could use -V where I've put -- virtual size. Let's make it 1 gigabyte. Now remember, we only have a pool of 100 megabytes. So will this work? Well, yes, it will, because what we're doing here is provisioning, not allocating. The minus thin says this is a thin volume, as opposed to what we used earlier was -- thin pool. And that is, of course, data_vg sparse_pool. And we therefore now need to give it a name so that we can refer to it in future. So let's call it sparse_volume, somewhat predictably. So we're going to create a volume called sparse volume in sparse pool with a virtual size of 1 gigabyte. Now immediately it's thrown up a warning, not an error. We expect this. And of course what it's telling us is that we have provisioned more space than we have allocated. So it's warning us that our thin volume size of 1 gigabyte is larger than the sparse pool size, allocated size of 100 megabytes. It also says we have not turned on protection against thin pools running out of space. So, well, it's good news that there is protection if we want to enable it. And of course we will. In other words, we can make our thin pool grow to accommodate the size of storage used by our end users, the enemy. Okay, in fact, let me clear the screen, it's getting a bit busy, and run the LVS again. We can see that our sparse volume has a capital V in the type, which stands for virtual. Capital V for thin. Okay, but we know what it means. Also, notice it tells us that it's in the pool, sparse pool. Okay, we can see that here, that it's under the pool column. It also has 0 in the data column, so that again, this will tell us how much space we are using on this device. You can imagine if we use 10% of our 1 gig, it would say 10% here, but 10% of 1 gig is 100 meg. So here it would say 100%. And we'll see that in a second. We're going to actually demonstrate all these wonderful things. Right, so first thing we should probably do is make this sparse volume usable in some way. So let's put a file system on it. So make a file system of type ext4 on our sparse volume. That was quick. I was about to say this may take a second because my disks have probably all fallen asleep, but apparently not. So let's now, in fact I have previously created a directory called thinpool, or thinvol, because you're not going to believe this, but I actually do kind of rehearse what I'm going to say to you. It may not seem like it, but I do actually go around and check that I kind of know what I'm talking about, or at least I hope I do. So we do have a directory called thinvol. So let's mount. So we now have if we have a look, we have a volume mounted under thinvol. What we now need to do is clear the screen so we can see what we're doing. Remind ourselves, let's actually get a command up that we can recall. So let's now go to user bin. Why? Well, because user bin is reasonably large but not ridiculously large. So what I'd like to do is copy everything in user bin into /thinvol. And the easiest way of doing that is just to do a copy. So if we copy star to /thinpool, thinvol, and do an ls of thinvol, we see that we have a copy of our user bin directory, which is pretty cool. And if we do a df-h of /thinvol, it says that it's currently used 344 megabytes of its 1 terabyte. So clear the screen, let's recall our LVS command, and we can see that our 100 megabyte is completely used, whereas our sparse pool has only used approximately 10% of its space. So that's fine. So why hasn't this all gone horribly wrong, I hear you ask? Well, let's do a journal CTL and look at the end and see what messages we have. And straight away we have a whole load of error messages. Buffer IO error on dev dm1 logical block blah. It says, it's basically saying there are a load of unwritten extents, so the end user at this point doesn't actually realize that we have a horrible problem. So let's do a sync, which will flush our buffer cache onto disk. And now let's do a journal CTL again, and it's complaining like crazy. So let's now go to /thinvol and let's try and create a file, and we've suddenly got an IO error. So something has gone horribly wrong, and that's not surprising. We've run out of disk space, and we should of course have been monitoring it and keeping an eye on it, and if the end user had got close to using all the disk, then we should have done something about it. So let's do something about it now. Let's actually unmount, we're in the directory, so we've unmounted it. So obviously we have a problem with that volume. That volume is in an unknown state. Okay, if we try to mount it again, so let's try mounting that volume. Okay, it can't read the super block. It's actually corrupted. It is completely knackered, to use the technical term. So we're going to have to MKFS it and start again. The problem was not the volume's fault. It was that we weren't monitoring our disk space. So first of all, let's MKFS it. It's warning us that it has been used, and we're saying no, that's okay, carry on. Okay, so let's now remount it, and let's have a look inside, and strangely enough there's nothing in there. Well, that's not a surprise at all. So now let's enable protection and then repeat that whole exercise. So to do that, we need to edit a file called etc lvm.conf. Okay, and if we go in there and search for auto extend, now that's actually a snapshot auto extend, so keep that in the back of your mind, because in the next section we're going to cover snapshots. But what we're interested in is thin volume. Here we go. All right, so this is incredibly well commented, which sometimes is a bit of a pain because it means you have to end up having to read an awful lot of text. So let me summarize for you. What it's saying is you've got two options. One of them is a threshold. So the threshold in this case is by default, it tells us here somewhere. Setting this to 100 disables automatic extension. If we look down here, it says it is set. So thin pool auto extend is set to 100 by default, so it's disabled by default. So what we want to do, we want to enable it by saying our thin pool auto extend threshold. That's the point where we start to worry about the state of our thin pool. The thin pool's hit 70%, so we're going to start getting notifications, and maybe something else will happen. So now let's go down and find the next setting, which is if we say our threshold is 70%, what happens when we hit that threshold? And what we're going to specify here is by how much would we like to increase or auto extend our pool. So here we uncomment that and we say thin pool auto extend percent equals 20. So these are the values that they have in the comments, and I'm perfectly happy to go with those. So what will happen is when our pool hits 70% of its capacity, then we will extend its size by 20%. We can save this file. Oh, by the way, it also, let me go back in there. It says automatic extension requires DM event daemon to be monitoring the logical volume. It will after we've made these changes. So let's save this now. The only thing is we need to actually tell DM event daemon. I mean, if we do a pgrep minus a, otherwise it just gives us the number, and we can see that that's the command actually running. So we can run DM event d, and we can use an option minus capital R, which basically says reread your configuration. We do that, okay. If we now do a journal CTL again, we will cover journal CTL at some point. Okay, and if we look here, whoops, if we look here, ignore errors up here, I'm getting errors on my USB interface. It says monitoring RAID device R1 vol, R10 vol, R5 vol, R6 vol, and importantly data VG sparse pool. So by restarting it, we now have it monitoring our storage. Okay, so let's recall our LVS command and have a look, and we'll see that we've already used 33% of sparse pool simply by creating a file system on it. Okay, so sparse pool is 100 megabytes, sparse volume is 1 gigabyte, and what we need to do now is break it. So let's mount it. So if we mount, okay, now we're going to cd2/user/bin, quickly do an ls of /thinvol to demonstrate that it is actually empty apart from loss plus found, and we're going to do our copy again. This is, do you remember last time? This is where everything went horribly wrong. Okay, because we didn't have enough space to copy a few hundred megabytes of data into thinvol. Okay, fine. That appears to have worked okay. So let's now cd to /thinvol, do an ls. It appears to have worked okay. We have a copy of everything in user bin. But how can that be? We've only got 100 megabytes of storage. So let's recall our LVS command. And whoa, look what's happened. Our sparse pool has suddenly increased to 572 megabytes. So it's increased in size dramatically. And we can see that we have actually used 37% of our 1 gigabyte. Okay, so just to remind you, what did we do? We edited, etc. lvm.conf. We searched for thinpool_auto_extend, and we uncommented the threshold and the auto extend size, and that then we had to restart the dm event daemon by doing dm event d -R, and we then deliberately overused our allocation because we had a provision of one gigabyte, so that's okay. So we deliberately forced dm event daemon to increase the size of our DataVG sparse pool volume. So there you go. That's thin volumes, and that's all I really want to say about that for the time being. Hope you found it useful.